Hi everybody, today's video I'm going to show you how this pulse motor works in the way I designed it. I'll be going through each component and the wiring configuration of this setup so you can get a good understanding of its layout, plus a bit of a live demonstration and going through each processes of each stages of how each pulse motor driver circuit somehow complements and assists each other, whether it is the flyback energy or the mechanical torque that's doing the work. This is a driver circuit schematic that's been originally designed by Wind Power More. If you haven't checked out his channel or went through his schematic or built any of his work, I highly recommend you do so. He has also some excellent valuable gemstone information with a lot of wisdom and knowledge on how to fine tune it, along with the troubleshooting techniques and understanding the oscilloscope readings to get the most out of it. And it's because of his videos and his generosity that's sharing to the community what helped me to push the boundaries for my pulse motor. So a big shout out to him. Thank you so much. And yeah, it's enabled me to keep pursuing this project. I've made some replacement parts to this driver circuit. So I've replaced the MOSFET, which is an NPN IRF 3205 MOSFET. I've connected 3 in parallel, and I added 1 or 2 watt carbon 33k resistor, so a 1 watt carbon 33k resistor where I just add 2 or 3 of them just so you can handle the current. And it's very important that you get the right resistance value for your gate drive as where the gate and the source is connected, because even with the most powerful voltage amp rated MOSFET along with its fast switching capabilities, without having the right rated matching resistance for the gate drive, you're going to be suffering a lot of heat build up and potentially blowing up on you and not giving it a nice pronounced sharper switching. And yeah, so I've learned that through the learning curves of experimenting with it, and I thought I might share that in case those that are interested. I've also replaced the previous non-polarized ceramic cap with a 223 3 kilovolt non-polarized high frequency ceramic cap. This pretty much dictates your performance of the driver circuit in combination to the setup of your coils and your rotor. My rotor has 12 magnets and they're all N52 grade. Each magnet is 50 millimeters by 30 millimeters thick, and it is set in the hallback array. And how did I do that in that sense? So what you got to know, and a lot of people might not know this, is that when you have a cube magnet, you have 2 north poles and 2 south poles, and each north pole, so you have a one north pole that it is stronger than the other north pole, which it is weaker, and same thing with a stronger south pole and a weaker south pole. So I use a Gauss meter, and it can measure the intensity of the flux of where you position it on each side, and every single one of these magnets is facing where it is at its most strongest side, and the back of it is slightly touching with all the other magnets, so it creates literally a whole back array. So I found that to be of great value to know that, because people might have a cube magnet and set it onto the rotor and not knowingly where it's not distributing an equal field strength as you hope. Also having a thicker, larger cross-sectional diameter copper wire. So this is 6 millimeters thick. I made a mistake on my previous video thinking it is Litz wire. It is actually braided wire. It is 15 meters each, and they're both connected in series. And the size and the geometry is very important because you're increasing the field area for the alternating collapsing in the magnetic field to propel this rotor, and it has a lot of great significant performance to that too. So in the ratio to your setup and to your driver circuit, it all comes to dabbling and experimenting how it works for you. So yeah, I just thought I'll share that. If you want to take a snapshot, go for it. And yeah, now I'll walk you through each component. So this is the primary driver circuit for this pulse motor setup here, and you have the input to start off with through the power supply, and you have the output flyback energy that gets dumped into these 16 volt at 350 farads, both connected in series. And the prime purpose for the first stage is to pretty much rely on the higher conversion rate of the flyback energy to quickly and rapidly charge those capacitors while increasing the frequency of the RPM to that rotor. And then once you reach to your desired level of your charging, so this one's happened to be connected together, it's around 33 plus volts. If you happen to have a 24 volts and you're at that limit, then from that point you kickstart and activate the second stage. And I've connected these two jumper leads, which is connected, those two jumper leads connected to these two larger coils here. And then you got these other two black leads that's connected to the input to the AC power transformer. And if I bring it closer, that's the voltage for the input, so 15 volts in. And then you get the 240 volts out. And one side of the lead has got a bridge rectifier, which is 1N4007. It's positioned and faced in a particular way, so it becomes like a half wave rectification that charges this 40 volt at 68,000 microfarads, which then becomes the power supply and feeds power to this secondary pulse motor. And the secondary pulse motor has its own motor coils, which is these 4 magnet wire coils. So you got the 2 at the back and the 2 at the front, and the coils on each side are another set of coils that it is not connected to the system yet because it's not completely done yet, and there are further ideas that I'm going to exploit and making use of what's available. So these 2 at the front and these 2 at the back are all connected in series. There are pretty much the diameter size wire is 0.75 millimeters thick, which is 20 to 21 AWG. Each coil is rated around 12 to 15 ohms, depending, it's not all exact, it's kind of slightly differ, and they're all connected in series. And you have the output flyback energy where the long leads get fed down all the way down, and it gets dumped to this separate 40 volt 68,000 microfarad can capacitor. And that is for later on, as I'll demonstrate, is intended to feed itself in when you get to the last stage. I call them stages because it kind of breaks up each process so people can get a good idea of what I mean. Well, I hope anyway. And once you have these 2 pulse motors and you got the RPM and the frequency set, and you're satisfied with the accumulated voltage that you've charged from the very beginning that costed you, then you start to begin and switch on this pulse motor / generator setup. And you have the output of these capacitor that gets fed through the switch, which then activates this driver circuit, which the oscilloscope probe is connected to the drain while the ground is connected to the negative of the input, so we can get an output reading. And the magnets arrangement for this rotor, so it is 20 millimeters by 10 millimeters thick. It is triple stacked, and each rotor has 12 magnets, all facing north and south pole. So it's hard to see because the plastic former that's sitting surrounding of the idler, which I found in the hard rubbish, there's 3 pretty much stacked inside of that plastic former. And the other one is the same, and I use kind of like a piece of metal that acts like spokes, where I'm enabled to bridge those 2 magnets together. So adjacently positioning each other, they are both north, both south, both north, and so forth. The coils, one of the coils is a trifilar. The strand diameter size is 0.75 again, or 20 to 21 AWG. It's got laminated silicon metal sheet that I've extracted from a microwave transformer, and I cut it into the size where it fits inside the core using tin snips, and then I epoxied it a few times. It's hard to see it. This one you probably get to see it, and then I epoxied it. And this one is just a single strand wounded coil. The front of the flange kind of snapped, but it's still usable. Each of these strands are all connected in parallel to each other. Even this coil as well is also connected parallel to this coil. And having these laminated silicon sheets has significantly reduced the eddy currents, and I've been getting a really good generous amount of current for what we are paying for. And the output flyback energy gets dumped onto these two 40 volts at 68,000 microfarads again, but they are both connected in series, which is connected to the watt meter, and the output to the watt meter is connected to this 100 watt 24 volt DC motor. So also with all this circuit that's been explained, also we have this high voltage step down converter module that I created, so that way we can also exploit the mechanical energy by using these two higher turn thinner gauge pickup coils. So each coil can vary anywhere from 25 to 27 ohms. It's 31 gauge, and they're all both connected in series, where the wires gets traveled and fed up from the above, and it goes to this 500 volt 30 amp bridge rectifier, where the DC output gets dumped into these two 450 volts at 25 microfarads AC capacitors, both connected in parallel, which the output of that energy gets fed through this step down high voltage converter into 24 volts. Depending on the speed on the RPM and how well you position your coils, if you get a good anywhere from 1 to 2,000 RPMs, and hypothetically having a good a dragless system where you're not impeded by the slowing force of the lens effect, then hypothetically you can get anywhere from 3 to 5 watts output from every 1.5 seconds pulses. So in a way it behaves like a cap dump, but it is not, because it only releases significant pulses when that reservoir gets charged, and that all depends on the amount of pickup coils you position and the RPMs you generate, because it is frequency dependent. And the purpose of having that up there is not to run loads. I've connected the 100 watt DC scooter motor in there, so I can see the rotation of the axis of each pulses. Also to time it as well and understand how pronounced it is. So at the moment it's probably turning anywhere from 30 to 40 degrees, where when I made the most of the speed and the RPM and tuned everything to harness most of that pickup coil energy with minimal drag, this was able to rotate anywhere over 200 degrees rotation. And these pulses hopefully will get dumped back into this ultra capacitor system here, because if we can keep this on the float, then this will pretty much run for a very, very long time. So without further ado, let's get right into it. I'll turn on the power supply. Alright, I've turned it on. It just needs a bit of a flick. Slowly will start building itself up. We'll increase the current because it's really at the low side. Now the prime purpose of using this primary driver circuit to this pulse motor is to rapidly and increasingly charge this ultra capacitor from the very as quick as possible. And that's why if you happen to be a bit more generous of increasing the power input, don't let that discourage you. It won't last for a while and it will make up for it in the long run. because it is a mechanical oscillator. It's not a solid state. So it's one of those gradual exponential growth situation when you allow time to do its thing. I'll turn on this multimeter back on. Now, because these two 16 volts 350 farads is connected in series, it's obviously going to be a lot more higher than a standard 24 volt battery. So in a hypothetical situation, just say you're content of how much you've charged and it's sitting around the 24 volts, and you've increased enough RPM for it to do some significant work, then we'll begin to activate the second stage or turn on the next pulse motor system. And the way how I do that is to make use of your input current by me adjusting this 50k potentiometer here. And I'm slowly just turning it in an anti-clockwise direction, and you can see it's reducing the input current. And you want it where it's sitting anywhere between 60 to 80 milliamps. And then while we've got the momentum going, it's time to connect the AC power transformer in. And as you can see, it has now jumped back up to 200, anywhere from 200 to close to 300 milliamps. It's now drawing 500 watts. Now the AC motor coil energy is now running the AC power transformer to 240 volts, is now in its pulsating state. It's charging this 40 volt 68,000 microfarad capacitor, and you can see it slowly climbing up its voltage here, which is now powering this pulse motor. And I can already hear it. It has picked up the RPM just a bit, and you can see how much power we are drawing. Now what gets interesting from here is I haven't even turned it all the way up, and like I said earlier, I believe is the whole purpose for this secondary pulse motor driver circuit is to make use of 70 to 75% torque energy transfer to help assist the drag what's yet to come with the pickup coils. Not to mention to alleviate the input current, which is now we are drawing anywhere from 3 watts, and we're getting the same propelling mechanical work as we did before. But because we've compensated the energy, the flyback energy that's been divided to do other area of work, this slowly gets trickle charge rather than the quick rate, because I've used that conserve energy to do some work in other places, which in this case operating this pulse motor and charging this DC cap. So now what we could do next, we are climbing up into the voltage, and now we're going to increase the RPM even more without affecting the power input. And by me doing so, I start adjusting this 100k potentiometer, and I'll start cranking it. And once you start cranking it, you can see it's going to be drawing power from that capacitor by dropping it. But in exchange, we are now increasing even more RPM to the system. As well, we're getting an additional flyback energy that's charging this other separate 40 volt 68,000 microfarads. And yeah, and that's the second stage of doing that. And you can adjust these two circuits in phase by playing around with it and seeing the ratio of your charging rate that you're charging your other devices, whether it's a battery or a capacitor or your resistive loads, in conjunction with the mechanical energy and the speed and RPM that's working on that too. And now we'll move on to the next stage. So just say you're happy with the voltage charge that you got from your battery or your capacitor of some sort, then we'll begin to turn on this pulse motor generator. I've got the oscilloscope probe, so the probe tip is connected to the drain of the MOSFET, and the negative ground is connected to the input negative as well. So in case if anyone wants to know how I read the output of this device. So now we'll begin to kickstart the other system here. I mean, I usually let it charge all the way up to 30 volts so I can make it last even longer. But in this instance, just for this demonstration, we're going to do a lot sooner. So I'll hit the switch and I'll try to give this a good yank. And here we go. There's the waveform of the oscilloscope that's reading at the moment. That's the output we're putting. Now that permanent magnet generator is getting fed. It's a three-phase generator that gets fed through this two parallel full-wave bridge rectifier, which is also charging energy to that to increase the charging rate even quicker. And you can see the comparison of the input current in comparison to the output current, and the minimal input current and well balanced it is, then the longer the system this will run, and this will drain a lot slower when you increase the input current even greater. And then just say this reservoir is ready to piggyback the system, then you obviously want to turn off the power supply first or anything first before you switch on that so there is no short. Disconnect that, and then I hit the switch. As I was explaining it, it adds a bit of a drag to the generator to supply energy to these rotors and to everything else. And that's what's still producing out from this output from the third driver circuit. This is now what the waveform looks at. This capacitor cap is now it's all self-looping now, just in case you kind of missed it. So it's all self-looping. It's still producing that AC transformer, it's still providing a bit of juice for that to keep the pulse motor going on the top, drawing minimal power as we're showing in the display on the reading of the input power. And it's now draining these capacitors, and it will keep going for good anywhere half an hour to 40 minutes before it gets really sluggish and becomes it falls apart. But yeah, so the next step is to exploit and make use of these high durated pulses, and I'll be implementing these unique type capacitors. These are lithium ion capacitors, and I've been doing a lot of research on them, and this can have a quick rapid charge and have a very slow discharge rate with very low leakage energy, and they're very great. So once I rely on these interval pulsations in the right rate with the right energy that's getting produced, then this is going to be charging that, which will help facilitate and get boosted with another booster to run other components, which, you know, the discharging will become very, very slow, and it will be like an equivalent of using a battery in the way of how it is placed under the load. So yeah, so I just thought I'll show you. It's right where it's at. So that's pretty much it. Still got a bit of a way to go. I mean, it's almost finished, but when I mean that, it's not necessarily finished. I mean, this is a continuous ongoing project, but as far as the building and the parts concerned, you know, it's pretty much close to where it's all about balancing it and fine-tuning it. And yeah, so I thank you very much for having a watch and I'll keep you updated for any further progress, and yeah, speak to you next time. Cheers.